Limits are an important concept in calculus, and today we'll be looking at a graphical approach to limits. Suppose you were to graph this function, x cubed minus 8 over x minus 2. We know that x cannot equal 2 because that would cause our denominator to be 0. However, it will not result in a vertical asymptote because we can factor our numerator and actually cancel the common factor of the x minus 2's. That would just create a hole in our graph, as we can see drawn here. For all x values not equal to 2, we can use standard curve sketching techniques, but the curve is not defined at x equals 2. As we saw, there's a hole in the graph, so let's get an idea of the behavior of the curve around x equals 2. We're going to be looking at what the y values are a little less than 2 and a little greater than 2. We're going to use our calculator to help us complete this chart. Plugging in these x values, notice how these are a little below 2. We'll be plugging in x values also a little above 2. Going to your calculator, you can go to the y equals and type in the rational function as you see here. Make sure that you use parentheses around the numerator and denominator. If we go to the table feature of the calculator, we can get there by pressing second window, and your table setup is probably set to auto for both the independent and dependent variable. We're going to go down and change the independent setting to ask. That's going to allow us to type in the x value that we want, and the calculator will tell us the corresponding y value by plugging into that function that we typed into the y equals. Now to go to our table, we'll get there by pressing second graph. And you should have an empty table allowing us to type in the x values that we want. So let's start with our x value of 1.75. Notice how as we're typing it shows in at the bottom of our screen. Press enter to make it show up in our table, and the calculator just put that into f of x and gave us our y value. So let's continue doing that for each x value the table asks for. As we're going along, go ahead and record these y values into the table on your paper. Now let's see what happens if we were to type in 2. 2 is the value that makes our denominator 0, so the calculator is going to give us an error. It should be obvious that as x gets closer and closer to 2, the value of f of x gets closer and closer to 12. So just under 2 is a tiny bit under 12, a little bit above 2 is a little bit above 12, and so we can say that the limit of f of x as x approaches 2 is 12. And this is written like this: limit as x approaches 2 of our function equals 12, or we can rewrite it replacing the f of x with the actual function. The informal definition of a limit is what is happening to y as x gets close to a certain number. In the last problem, we saw as x got closer to 2, what was happening to the y values is that they were getting closer to 12 on both sides. In order for the limit to exist, we must be approaching the same y value as we approach some value c from either the left or the right side. If this does not happen, we say the limit does not exist as we approach c. If we want the limit of f of x as we approach some value of c from the left-hand side, we're going to write it out like this. And notice how there's a little negative up in the upper right corner next to whatever this number is. If we want to find the limit as we approach the value from the right-hand side, we'll do a similar notation, but that's going to be a little plus sign instead. So in order for the limit to exist, the limit coming from the left side must equal the limit coming from the right, and then we would say that our limit is whatever that y value is. So let's start to look at a few examples. In example 1, first it's asking us the limit as x approaches 1 from the left. In other words, as x is getting closer to 1, coming from the left side, the y value is getting closer to 1. Now the limit as x approaches 1 from the right side. We're going to be coming up here. We see the y value is getting closer to 2. So because these two are not the same, we can say the limit as x approaches 1 does not exist because it's not the same y value coming from the left and the right side. Another question that's commonly asked in this series of questions is to find the actual function value when x is equal to 1. That's going to be here where the point is filled in. And so we see the y value for that point is equal to 2. The open circle indicates that the y value was not there. It can't be a closed circle in both locations because if we think about the definition for a function, it has to pass the vertical line test, meaning if we draw a vertical line through, it's only going to pass through in one place. Let's look at the second example. The limit as x approaches 1 from the left-hand side is negative 1. The limit as x approaches 1 from the right-hand side is positive 1. Similar to the last problem, because they're not the same, the limit as x approaches 1 does not exist. Now, let's look at the function value when x equals 1. Now the filled-in dot is right there on top of the x-axis. That y value is equal to 0. Go ahead and turn over to the next page. Let's look at example 3. Now we're going to approach 1 from the left. The y value is approaching 1. As x approaches 1 from the right, the y value approaches 1. Since it's the same number, we say overall the limit as x approaches 1 from either side is equal to 1. Also, f of 1, the function value when x is equal to 1 does not exist because it's just a hole. We don't see anywhere on the graph. We don't see the closed circle, so it does not exist. All right, example 4 is very similar to example 3, but notice how we have this filled-in circle here. That's going to change our answer for f of 1. F of 1 is this point down here, negative 2. Everything else will stay the same because everything else about it, it's the same picture, same graph, and they're asking us for the same limits. All right, in example 5, now x is going to approach 0, which is right on top of the y-axis. X is going to approach 0 from the left side. The limit is 1. As x approaches 0 from the right side, the limit is also 1. So overall, as x approaches 0, the limit is 1. F of 0 is also equal to 1. If it just looks like a smooth continuous curved line, we can assume that is a closed circle right there. We don't see an open circle, so we can assume that the function value there is a point that exists right there. Let's look at example 6. Now we're looking at limits as x approaches 2. First, going as x approaches 2 from the left side, notice how our limit, it seems to be approaching a very large y value. This sort of looks like an asymptote that we would see in the graph of a rational function, and so we can say that it's approaching a positive infinity, which is a way to say a very large number. Looking at the other side as x approaches 2 from the right side, now it's going downward, approaching a very, very small number, which we can call negative infinity. Just as we've seen in the other examples, because it's not the same, overall the limit as x approaches 2 does not exist. Also, the function value when x equals 2 does not exist. We don't see any solid points. At x equals 2, it's just an asymptote line. In example 7, the limit as x approaches 2 from the left is positive infinity since that curve is going upwards. The limit as x approaches 2 from the right is also positive infinity. It's going in the same direction. So because these limits are the same, overall, the limit as x approaches 2 is positive infinity. I'm sorry, I said 2 every time. I meant to say negative 2. Finally, similar to the last one, the function value when x equals negative 2 does not exist. Because it's an asymptote, we don't see a point there. Let's look at example 8. It's almost the same as example 7, but there is a point here, so that's going to change our answer for the f of negative 2. That y value is 0. The other answers will stay the same. Now, the concept of limits as x approaches infinity means the following. What happens to y as x gets infinitely large? We are interested in what is happening to the y value as the curve gets further to the right. We can also talk about limits as x approaches negative infinity. This means what is happening to the y value as the curve gets farther and farther to the left. The terminology we use are the following. Limit as x approaches infinity. That's looking what happens as we move further right. The limit as x approaches negative infinity is what happens to the y values as we go further left. Though we use the term as x approaches infinity, realize that x cannot approach infinity, as infinity does not exist. The term x approaches infinity is just a convenient way to talk about the curve infinitely far to the right. Note that it makes no sense to talk about the limit as x approaches infinity from the right side or from the left side. We can't approach infinity from the right or left because infinity is not a value. It's not a specific number like the other examples that we've seen. We can approach 2 from the left or right, but we can't approach infinity that way. Now it says here there are only 4 possibilities. I'm going to have you cross that out and change that to 5. We're going to add 1 to the end. 5 possibilities for the limit as x approaches infinity or negative infinity. Let's look at the picture in example 9. It says that the curve can go up forever. In that case, the limit does not exist. For convenience sake, we will say that the limit as x approaches infinity is equal to infinity. So let's see how that compares to our picture here. So the limit as x approaches infinity is what's happening as the x values are getting infinitely large. The y values are also getting infinitely large. So approaching positive infinity, a very, very large positive number. In this case, the limit as x approaches negative infinity, as the x values are getting smaller and smaller, the y values are still getting larger and larger, so that limit is also infinity. All right, a second case, the curve can go down forever. In that case, the limit does not exist. But for convenience sake, we will say that the limit as x approaches infinity, so in this case, look at what's happening on the right-hand side. The y values are going down forever, so we'll say they're approaching negative infinity, which is a convenient way to say a very, very small number. In this case, as x approaches negative infinity, looking at the left-hand side of our graph, the y values are continually going upward, so we'll say that it approaches positive infinity again. All right, a third case is that the curve can become asymptotic to a line. In that case, the limit as x approaches infinity is a value. It's a specific number that we can state. And so in example 11, it looks like there is a horizontal asymptote at 1. As x approaches positive infinity, the y values are approaching 1. And down here it appears to be an asymptote at negative 1. So as the x values approach negative infinity, the y values are approaching negative 1. A fourth possibility is that the curve can level off to a line. In that case, the limit as x approaches infinity is also a value. So we see as x values are getting bigger, the y values are getting closer to 0. As the x values are getting smaller, the y values are getting closer to 0 again. The fifth case that we're going to add is if we have a graph that oscillates, similar to the graph of sine or cosine. In this case, we'll simply say that the limit does not exist. As the x values get increasingly larger, as x approaches positive infinity, the y values would always be going back and forth between, for example, if this was the graph of negative sine, they'll consistently be moving between negative 1 and positive 1. It's never going to level out to a specific number, so it just simply does not exist.